Welcome to this week's Origins Colloquium. It's a great pleasure to have Phil Armitage giving the talk this week. Phil literally has written the book on planet formation. I learned what little I know about planet formation from his lecture notes originally, which I think became this fantastic book when I was starting to get involved in planet formation. And as we were just chatting, he did his undergraduate and graduate work at the University of Cambridge, worked with Kathy Clark there at IOA, and was then a postdoc at CETA and MPA, a lecturer at St Andrews, and then a professor at the University of Colorado until 2018, when at that point he moved to join CCA and Stony Brook, where he, at CCA in particular, leads the Planet Formation Working Group. So it's a great pleasure, Phil, to welcome you this week.
Thank you. What I want to talk about is some work we're doing on circumplanetary disks, and the sort of basic questions we're trying to address from a theory point of view, how they form, and then there's sort of some relation, I think, to an observational question, which is sort of why don't we often see them, or why don't we see more circumplanetary disks? So to sort of give just one slide of very general introduction, the idea that Jupiter's Galilean moons form from a disk, sort of analogous to the solar nebula, is extremely old, right? So I think in introductory astronomy classes, a common thing we often say is that the Galilean moons look like a miniature solar system. And that's not like an original thought. So Kant, in 250 years or something ago, basically said pretty much exactly that. And so it's sort of, I guess, been assumed from that time that there was a proto-Jovian nebula around Jupiter from which the Galilean moons formed. And there's some evidence for that, or some things that would be consistent with that, to do, for example, with the mean density of the Galilean satellites. It goes from high to low density as you go further out, suggesting increasing the icy compositions. However, in terms of direct detections, PDS-70C was the first detection of actual detection of a circumplanetary disk, now 5 years ago, and that remains basically the only sort of secure detection we have today. So what I'd like to talk about in these 30 minutes or so is just a little very general introduction with some sort of expectations, and then just one slide on those observations of PDS-70C, and then talk about two projects we've done recently addressing some physics aspects of circumplanetary disks from the point of view of simulations, one of which focuses on sort of simplified hydrodynamics, really just trying to look at the effects of planetary mass and disk scale height. So it's been led by a graduate student at Stony Brook, Sabina, and then a more complicated sort of physics complete project led by Leo Krapp, which is doing thermodynamics and radiation transport and so forth. And then I think, the final bit, why disk may be rare, will be sort of obvious once we've got through those things. So this is an abstraction of a longer talk. There's another question we've thought about, whether circumplanetary disks are accretion disks or decretion disks. So is the gas actually overall sort of flowing towards the planet or away from the planet in these disks? That's quite interesting actually for satellite formation. And so there's some other work we've done by Rebecca Martin I can talk about in discussion if we want to go in the direction of satellites. Okay, so let's start with very basic things here. We have a giant planet, so we're sort of thinking Saturn, Jupiter, super Jupiter kind of masses. A disk may form around that planet due to angular momentum accreted from the protoplanetary disk, while it's still embedded in the disk phase. And the characteristic scale is the Hill sphere, where the tidal gravity from the star matches the gravity from the planet. And if you sort of have classical results for disks in binary potentials, you expect them to get to about 40% of the Hill radius before they're tidally truncated. So that kind of gives you an elementary scaling for how big you might expect a circumplanetary disk to be. And some numbers have been put here on the bottom here for planet at an orbital separation of 30 AU, so already quite far out. relatively nearby star, 100 parsecs, Jupiter mass planet, and you get numbers that are about 10 milliarc seconds. So obviously, one reason why circumplanetary disks are hard to see is that they are very small. And that was like a cartoon picture. Here's one of Venus simulations, also for a Jupiter mass planet, and you can see it. It looks pretty much look like I was describing. So the basic picture you get from that elementary thinking is fine. So they're small, but then there's a flip side of that, which is you can ask, well, how much luminosity might you expect to get from that rather small region? So if you assume, let's say, that a Jupiter mass planet accretes most of its mass through a disk, it does so in 1 million years. That's a fairly generous amount of lifetime. It might be shorter than that. Then you have an accretion rate of 10⁻⁹ solar masses per year. The size might be twice the current Jupiter radius. And the accretion luminosity you get from that is about 10⁻⁴ solar luminosities. Okay, so if you sort of think about that in terms of sort of direct detection of exoplanets, direct imaging of exoplanets, the kind of contrast ratios you have there, this is a sort of super favorable contrast ratio, right? It's only 1/10,000th the luminosity of the star. So in that sense, circumplanetary disks, even though they're small, they could actually sort of serve as signposts for protoplanets, where what we would be seeing would either be the luminosity from the disk itself, or the sort of accretion luminosity as it joins the star. And these kind of arguments have been expanded on. Zhaoan had a paper now quite a long time ago going through some of these basic estimates. And there's one in particular to note, which is that if you assumed that gas accretion was sort of going onto the star in a T Tauri-like fashion, so with an accretion shock, you can predict an H alpha luminosity, and that H alpha signature would be really whopping and easy to see, right? So if you're getting a lot of this in H alpha, you would be seeing potentially these circumplanetary disks and the accretion signatures of protoplanets very easily. So those are some basic expectations. What do we actually see? Well, as I mentioned, there's this one case that is reasonably straightforward and convincing. So this is PDS 70c. The orbital separation is about 30 AU. It's a young star, not so different in mass from the sun. And there are two giant protoplanets there, probably of a few Jupiter masses. And together it seems they've carved this large cavity in the gas and dust disk around it. And ALMA data at 855 microns indicates that there is some emission, dust emission, continuum emission from the location of PDS 70c, which would be sort of consistent with the expected size of a circumplanetary disk in that place. That would be about 1 AU. And the amount of material there depends very much on what you assume about the grain size. But it's not so far different in mass from what you would get for the Galilean satellites. I mean, smaller, but not orders of magnitude smaller. So this is in some sense quite encouraging. So the properties of this candidate, very strong candidate circumplanetary disk, are roughly as predicted. And
what is the sensitivity on the amount of material around PDS 70b then?
I'm actually not sure what that limit is. Mm-hmm. Yeah, I don't know. That's an interesting question. Mm-hmm. But yeah, if you look back then, like Zhaoan's paper, of course, this actually shows the amazing, in principle, sensitivity we have to circumplanetary disks, right? Because here there's a system where the solid mass is smaller than the Galilean satellites. Even actually for sort of favorable assumptions about the grain size, but it's detectable. So this is what we have, and I would say there are a small number, really a small handful of other candidates seen in either continuum or molecular line emission, but none of those are, I would say, sort of fully or widely accepted. So is that a puzzle? Well, maybe yes, maybe no. The place that maybe does seem as if it's a little bit of a puzzle is that there's an entirely separate line of evidence that I'm sure you've all heard of many times, suggesting that disk-embedded protoplanets might be very common. And in particular, they might be surprisingly common at sort of the same sorts of separation, 30, 40, 50 AU, as we see for the PDS-70C system. And this is a gallery. This was a Quantum magazine article just showing a bunch of ALMA substructure observations, rings, spirals, these sort of crescent-shaped features. And all of those, as you know, have plausible, maybe sort of a favored explanation in terms of planetary-induced structures. Okay, and those are come to, those may not be really massive giant planets, but they're also not Earth mass planets. So they are in sort of the regime where potentially they might have circumplanetary disks, and we might potentially see the emission. And clearly, we're not for the moment, seeing that emission very broadly. So that's sort of the introduction. So where does that sort of leave us? Well, on the one hand, if we think about sort of circumplanetary disk physics, it has some properties that are actually quite favorable if we think we'd like to understand physically what's going on in these systems. So, they accrete from an environment, which is protoplanetary disks, that is now actually quite well observed. And I guess is it better observed than the environment from which stars accrete? I mean, I think that's sort of something you could argue about, but it's sort of, we see disks, protoplanets are sort of orbiting probably on near circular orbits within gaps. We can measure something about the kinematics, the gas mass, the dust mass, and so forth. So we sort of know to some degree what the initial conditions for circumplanetary disks ought to be. However, it's also true that current observations do not strongly constrain disk properties at all, even in that PDS-70C system. It's barely resolved if at all. There's some crude mass estimate for the dust mass. That's pretty much it. So that's where things stand on the observational side. From the simulation side, it's an interesting problem, and it's quite a challenging one. So it certainly involves these sort of multi-scale aspects. So the scales of interest go from the physical scale of the planet, so Jupiter radius, up to the global scale. So that's a fairly extreme range of scales, certainly if you're at large distances. And then, maybe even more important, it's multi-scale in time because the circumplanetary disk was orbiting around the planet in quite a short period. The planet is orbiting around the star on a longer period. And then, as we'll come to, there's also the question of how quickly the gas might cool. And as many of you know, when you think about giant planet formation, how quickly the envelope cools is a kind of critical thing that kind of gets you to run away and then to later phases of giant planet evolution. And those timescales can be hundreds of thousands of years, something like that, right? So those are really very long timescales compared to any of the dynamic timescales. So we've been looking at this in a couple of ways. So the work I'm going to show that Savina has led is global simulations with very simple physics, very simple hydrodynamics. We've done that to do a small parameter survey. And then we've done a smaller number of simulations. Leo has led a smaller number of simulations where we try to do the best job possible we can with the physics. But that, of course, introduces a lot of extra parameters. And, we'll see that creates some extra complications. But I think the overall this is giving us some picture. So let me begin with this first paper, which was submitted a couple of weeks ago. So what we've done here is to consider global simulations. These are done with the Athena++ code. Quite simple, but they have static mesh refinement around the planet to give us reasonable resolution for a potential circumplanetary disk. And based on a large body of previous literature, if you want to maximize the chance of disk formation, it's clear that isothermal conditions or near isothermal conditions are the conditions that get you there, right? So this work now that goes back more than 10 years. If you do simulations of protoplanets embedded in disks with adiabatic equations of state, you basically never get circumplanetary disks. If you do them with isothermal equations of state, you do. So we've used a quasi-isothermal approximation, a gamma of 1.01 that is sort of almost the best case for forming a circumplanetary disk. And I say almost because, of course, you could imagine, not unreasonably, that the protoplanet and its circumplanetary disk are embedded within a gap. So it might be, but plausibly is, that that region is shadowed from the direct stellar radiation. So it's possible that the material around the planet could actually cool below the temperature of the local protoplanetary disk. So then it would be colder than you would get from an isothermal assumption. So we can discuss that limitation more later.
So no accretional heating.
So yeah, there's no accretional heating. Yeah. So there's no accretional heating. So that's indeed that's the flip side, right? It could be shadowed, but then the protoplanet itself would be hot and would provide its own source of heating, and so forth. And so in these simulations, the only things we vary are the disk thickness, h/r, and the planet mass. And really the sole question, or the main question, is when does accretion lead to disks versus instead sort of quasi-spherical envelopes around the planet, which might have some sense of rotation, but would not be what you would describe as a disk geometry. Okay, so here's sort of the answer to that question. So you've got left to right panels showing different planet masses, 0.3 Jupiter masses, that's about Saturn, Jupiter, 3 Jupiter masses. And then scale heights are 0.05, 0.075, 0.1. And these are projections in the radial vertical direction. Okay, so you're zooming in on the planet, and yeah, the equator in these images is where the disk would be rotating, and then the vertical direction is the up and down from the midplane of the protoplanetary disk. And if you sort of just eyeball these plots, I think you can sort of see that maybe the 4 on the left of that sort of diagonal line I've drawn look sort of basically sphericalish. The 5 on the right on very thin disks. So no one expects circumplanetary disks to be very thin, right? So that's an analytic expectation. But they do have a clearly flattened disk-like morphology. So that's sort of the basic dividing line one gets from this kind of simple calculation. And you can go a little bit further and look at the rotation speed of the gas around the planet. So this is normalized to the Kepler speed. So the inner parts turn over because we have a softened point mass for the planet, right? So we don't go anywhere near resolving the actual planetary scales. So you shouldn't trust the stuff on the left. But yeah, what you sort of broadly see is that in some of these cases, you get 90% or something of Keplerian speed at a couple of tenths of the Hill radius. In others, you are very, very sub-Keplerian, right? So you're maybe rotating a little bit, but you're not really anything like a disk. And how does this scale? Well, what we find is really exactly what you would expect analytically. If you think about the thermal mass, which would be where the Hill sphere of the planet equals the scale height of the gas in the protoplanetary disk around it. If you normalize the planet mass to the thermal mass, which has this quite strong scaling with h/r, then the parameters, the morphology basically scales with that ratio. So if you're subthermal planets, you end up with the envelopes. If you're superthermal planets, significantly superthermal planets, you end up with the disks. So this is sort of as expected. And so in some degree, then the game of the simulations is to work out, where that prefactor is. Is it 0.5 thermal masses, 1, 2, whatever thermal masses where the transition occurs.
I'm sorry I interrupt so much, but under this thermal mass, how does it compare to the gap opening mass?
So for typical parameters, it is similar, but the gap opening mass also involves the disk viscosity, or in fact, in some sense, primarily involves the disk viscosity, right? So I think if I remember the scalings right, the gap opening mass has h/r to the 2.5 rather than 3 at alpha to the -1. So it's similar scale height dependence, but then it also folds in the turbulence levels.
Right.
So if the disk was, so I think the basic answer is if we if we wind back to when people thought alpha was 10 to the minus 3 or 10 to the minus 2 in protoplanetary disks, then these masses are similar.
Mm.
If actually the turbulence level is lower, then you would open the gap more easily than reaching the thermal mass.
Mm-hmm.
So that's the direction it would be. So we also looked at some other things, which is just in the paper. You can take a look at them. Actually, the original motivation for this project was not so much to look at this question, but to look at what the circularization radius is. So this gas is sort of flowing in vertically in a three-dimensional way towards the planet. So we sort of wanted to try to measure where it would circularize. Is it really close to the planet? Is it further out? It has some particular scaling also with the thermal mass. We also looked a little bit at numerical convergence, which is not completely convincing, but is maybe not completely unconverged either. Okay, and the sort of basic result in terms of this question of morphology is that this threshold is about 2 under these sort of semi-optimal thermodynamic conditions. Okay, so that's what we find. So I think that's all fine. I'm sort of happy with those results. I would say, there is an immediate puzzle here, which is that, as I mentioned, these leftmost columns in these plots, so the left panels there are the ones you've already seen. The right ones are projections or slices actually in the disk midplane. So the red boxes there show the simulations we've done for Saturn mass planets, and we don't really find any rotation or significant rotation, making like a disk-like morphology for Saturn. Okay, so this obviously creates a little bit of a puzzle, maybe quite a puzzle for the solar system. If you look in the literature, you'll find actually that there are models for primordial circumplanetary disks, even for Uranus and Neptune. So I would say Uranus and Neptune are, way lower masses compared to anything that we would form a disk around, or anyone else would form a disk around, right? So I think those primordial models for particularly the regular satellites of Uranus are sort of strongly disfavored on these sort of theory grounds. But Saturn is a different story. There are nice regular satellites of Saturn. It seems very likely perhaps they formed in a primordial circumplanetary disk. And it's definitely, not in the parameter regime where we're finding disks. So there's some questions there about really what was going on with Saturn, which I don't have any answer to. Okay, so let me then just move on for another 5 minutes then to this other set of simulations we've done. And the basic point here is that that previous set were under these sort of near optimal conditions for making circumplanetary disks. But of course, if the gas is to remain isothermal as it's flowing in from the protoplanetary disk and joining the circumplanetary disk, then you need it not to heat up, or if it heats up, it needs to be able to cool down radiatively, right? Of course, the planet itself is, as Jonathan was saying, the planet itself is also going to be hot, right? So that's also a consideration, right? So actually, the ability of the gas to remain even near isothermal is very questionable, right? You have to really think about that. So Leo, in a bunch of work, actually developed quite a bit of the capability to model this kind of problem consistently in Fargo 3D. So there's a bunch of sort of technical aspects here that are really, I think, quite cool. So these simulations use radiation hydrodynamics in the flux limited diffusion approximation. But then the neat part is he evolves multiple fluids for the gas and a number of different particle sizes, and then computes the opacity which enters into the radiation hydrodynamics consistently from the local particle size distribution. So if you imagine you have these different particle sizes, some of them are settling, some of them are more or less affected by aerodynamic drag. So the local abundance of dust and potentially also its size distribution varies across the simulation domain. So you can then use that to compute the opacity and feed that directly into the radiation hydrodynamics. So these are, some of the first calculations, at least in this domain, which have that kind of coupling between the dust physics and the radiation physics. So here's just an example of what it looks like. These are again global simulations. Sort of quite use static mesh refinement, but they use a similar technique to squeeze the grid close to the planet. And then on the right, you've got a zoom in of where the planet is. In this illustration, just highlighting this sort of technical aspect that here you can compute the opacity field sort of consistently from how the dust, which is going to be the dominant contributor to the opacity, unless you get closer in and hotter, where you get a lot of molecules contributing. You can actually compute it as in a sort of three-dimensional way in a time-dependent way. So this is complicated. Is it necessary? So here's just an example of sort of three simulations you can do. So there's a standard case there. There's a sort of standard case doesn't have this coupling of the opacity to what the dust is doing. So that's one case. There's an isothermal case, which was very simple. That's basically what we did in those previous calculations. And then there's this multi-fluid case in the middle. And clearly, if you sort of look at this, again, these are radial vertical slices or projections. There are large differences in morphology between isothermal and radiative, so left and right. That's the same result that's now been known for 15 years or thereabouts. But there are also some differences between the radiative, which is the leftmost, and the multi-fluid. And those result from particle settling. So dust particles are able to settle to some degree. So the opacity in the sort of envelope, if there is an envelope around the planet, is not symmetric or it's not constant around the polar angle. It's typically smaller towards the poles and larger towards the midplane.
How many different size bins of dust?
We have like 6 or something like that. So it's a smallish number. It wouldn't be enough to do coagulation physics. So as you know, because we've been talking about here, we're working here at CCA to do some other ways of doing the dust that would enable you to evolve smaller numbers of fluids and therefore also say something about coagulation. But here we can't do that. So what did we find from these simulations? Well, what we were looking for was a sort of criterion for when you would get a disk and when you wouldn't get a disk, but now involving these radiative effects as opposed to just mass and disk thickness. And this has actually been studied a lot back to the early 80s for black hole accretion. So now the difference between a radiatively efficient disk that you get in an AGN or a quasar versus M87 or Sagittarius A star is generally considered to be the cooling time of the plasma. Right, so you get a thick, puffy torus structure if the cooling time is long, and you get a thin disk if the cooling time is short. So we were seeking a sort of similar criteria for these circumplanetary disks. How fast do you have to cool them in order to get a disk? If you are in the regime where, let's say, in isothermal conditions, you would get a disk, right? So it's going to be a necessary condition, but not a sufficient condition. And it's more complicated here than the black hole case, because the black hole case, you typically think of M87, Sagittarius A star. These are optically thin flows. So the cooling is really a sort of on-the-spot thing you can compute at different radii, right? Whereas here, these are flows that are partially convective, partially radiative, but they're generally optically thick. So what Leo found was that you can define a cooling time, which is sort of basically something like the amount of energy within a particular volume divided by the luminosity flowing through that volume. And the result was that sort of quasi-isothermal results can be recovered if the cooling time defined in this particular way is about an order of magnitude shorter than the orbital time. Okay, so bringing together the two pieces, what we would say is you need a massive enough planet compared to sort of the local disk thickness, but then you also require that the opacity be low enough that the cooling is fast enough on sort of this possible disk scale of about a third of a Hill sphere radius in order to form a disk. And so, these are just some plots. We were only able to do a small number of these simulations. They have some, other complicated time-dependent aspects that I would say we don't fully understand. So it's not not such a simple picture as the previous simulations. But we also looked at some prior results. Julius Ugali's done work on this. Aycliffe and Bate did work on this. Others as well. And we find that this sort of cooling time criterion, I think, is sort of broadly consistent with what's been published in the literature. Okay, so seems something like this. Maybe how you can describe these radiative effects. Now, an important caveat is that the equation I showed on the previous slide involves integrals and measurements of luminosity over simulation-derived quantities. Okay, so of course it would be nice, and something we tried to do was to make this sort of constructive in the sense, okay, I tell you the planet mass, the disk thickness, the opacity. From that, you calculate a cooling time in some way, and then say, yes, you have a disk, or no, you don't have a disk. And we didn't manage to do that, right? Because we have to do the simulation to measure what the cooling time is. So that's a limitation. And I think we probably need to go back and look at this with actually some simpler radiative physics in order to try to get towards that goal. So that was all I wanted to say. The big picture of things, the exciting thing is that circumplanetary disks have been detected for the first time. So that's really, to some degree, the big takeaway. Seems, based on what we've done, that actually the conditions for making circumplanetary disks are rather more restrictive than I guess I'd fully appreciated before. You actually need sort of quite massive planets, quite efficient cooling in order to make those systems. And so possibly the explanation for why we're not seeing more protoplanets in ALMA substructure sources is simply that, especially at large separations where the disk is relatively puffy, those conditions are just hard to meet, right? So most protoplanets maybe are large enough to generate structures, but not large enough to form disks. And so the accretion then still going on, but is embedded instead in envelopes. It's harder to distinguish from the disk emission.
Great, thank you very much, Bill. Plenty of time for questions and discussion. So if I know Joe at Chalmers and I guess you, Ryan, there can help me, or raise your hands in the Zoom. Let me ask a very basic question to start, though. If the planet is accreting, it's still a source of luminosity. It's still pretty concentrated, even if it's not a disk. So shouldn't they still stand out if the disk were not a disk?
Yeah, so I mean, I think that is the question. So of course, as you know, there's Aviarigo, right? So there are sources where there are overluminosities in the disk, right, which have been suggested to be protoplanetary accretion. So that, I think, is the kind of thing that's the kind of thing one's looking for, right?
But in your full physics simulation, are you measuring an accretion rate and a luminosity?
Here you can't really do that, right? So I think the problem is to do that, you really need to get close to the physical planetary scale, right? So that's the problem, because then you really need the potential well to be the proper depth, and then you also that's not out of the question to do, right? The trickier thing is that you also need to sort of run for long enough that you reach some kind of radiative equilibrium. And that's the part actually that kind of worries me a little bit more about trying to make full progress on this, that running for 100 orbits or even 1,000 orbits is potentially a short time.
But still, just from energetics, given some ALMA observation and some sensitivity to point sources, there's a for given planet mass that there's some limit on the accretion rate that's going on now in these systems, I think. Right?
Yeah.
And those numbers have been worked out then, have they, for these kinds of disks?
I'm actually not certain.
No,
So,
so
I mean, I guess we could, yeah, one could almost think of it on the spot, right? I mean, it's like, so, yeah, if you say you're making Jupiter, right? So you're looking at 10 to the minus 4 solar luminosities. If it's embedded within the disk, then it's sort of radiating on like the scale of the Hill sphere, or the disk thickness, actually, the disk thickness, right? So that would be, what, 1%, but less than 1% of the disk area, something like that, right? So that's not super favorable, right? 10 to the minus 4 stellar luminosities, 1% of the disk radius. It's not going to be, compared to the, just the irradiation.
Yeah,
it's not.
We can work out
we can work it out, but it's. So I guess the thing is, that's obviously what you got to look for, but it's not probably, it's not nearly such a characteristic thing.
Okay, any questions there in Virginia or Chalmers or online? Please raise your hands.
I had a quick question, actually. Thanks for the presentation. What radius is the PDF70B or C per circumplanetary?
So I think it's like 34 AU. I'm not sure if that's projected or correct separation, but it's quite far out there. It's like
okay.
34 AU.
And is that where it's far out for its disks to be more challenging to form, or is it just to clear? Is it even further out where you get the envelopes?
So the thing is, the PDF70C system, the mass is not, it's of course not very well known, right? But I think most people think it's quite massive, right? So maybe this is 3, 4, 5 Jupiter masses. So that would be fine, basically, based on our simple considerations.
Right.
There's also the fact that you've got these 2 planets in PDF70, so they made this really big cavity. We haven't tried to think about really what effect that would make. I think you might imagine that also helps a little bit, or maybe quite a bit, right? Clearly, imagine that disk there. It's probably not shadowed, right? It's in this big cavity, so it could probably radiate pretty freely to space. So
there must be gas in there that it's secreting from. So I know it looks quite black in this image, but there is a measured intensity there, is there, in the cavity?
So there's certainly measured stuff inside. I'm not sure how much. I'm not sure whether there's a gas measurement in the cavity here. I mean, some similar sources there is, of course, but I'm actually not sure in this case. So I think the basic answer to the question is that PDF70 is far out, but it's very likely to be a very massive planet, and so it would fall in a plausible place where you would make a CPD based on what we've done.
You found you have a question.
Yeah, so I'm trying to think. So sounds like if the most of the planets, if they are currently accreting, they're embedded, that gives sort of like a pessimistic view of if we want to detect them, like what's the best way. So sounds like the kinematic is maybe the way to go. So I wonder, given this simulation, does it give some new guidance about how to use the gas kinematic to find planets?
Yeah. So I guess we've not done that, right? So that's yeah. So we have not analyzed these simulations. So Leo has some follow-up work he's doing. I'm not exactly sure what he's doing there. I mean, I think the novelty in the radiation stuff is mostly in this sort of coupling of the dust to the radiation. May make some difference to the kinematics. How much I'm not sure. I guess stepping back from these details, I would say I guess my feeling about the kinematics is that a lot of that is a lot of the uncertainties there sort of amount from sort of the difficulties in doing that data processing and really making a kind of robust comparison with models, right? So I feel kinematics is tremendously, has enormous potential here, right? So I share this view that that's the way to go. I would be much more comfortable if it's possible to make, a statement. This disk has smooth kinematics. You can rule out a Jupiter mass planet at 50 AU with this significance level, right? And that at the moment is not something that, to my knowledge, is really possible very easily. So
Any other questions then? Let me come back to, while you're thinking of your questions, let me come back to this gap, the relation to the gap opening mass and so on. So in the ALMA images, there are all these gaps. So the interpretation is there are planets there massive enough to open the gap. And now you have a condition for when there should be a disk, which, this is another constraint. Although it's still not clear to me if, whether the disk or not the disk is not necessarily going to impact the observability as a point source, but maybe higher accretion rates are easier through a disk, I think, because your material has a chance to radiate away its energy. So let's assume that's right. So the gap opening just depends on the viscosity. So can you couple all these together and say, there's a planet, it's massive enough to open a gap, but it's not massive enough to create a disk. Therefore, the viscosity is something is constrained.
yeah, I mean, you could say that. I mean, I think such an argument would be much less direct and constraining than basically just looking at like the width of a ring, or things that people have looked at before the morphology, right? I mean, I guess there's another consideration which is sort of related, right? Which is that if the planet mass gets larger, above the point where it could open the gap, you might push into a regime where the gap edge is lossy wave unstable, and then it produces a vortex-like structure, right? And so you get into a different regime of substructure, right? So, so if you hold with the view that most of the substructure is planet sourced, then I think you would say, well, the systems where you see the sort of horseshoe-shaped structures, presumptively the most massive planets, those would also be the ones which would be most.
But then let me take a step back. So if I'm massive enough to open a gap, and you've got some estimate of the mass based on the width of these gaps, then are we in a regime where you would now think they should have disks or not yet have disks?
They could not. They don't have to have disks. So I think
they can open a gap, but not yet.
They can open a gap. I mean, of course, it's not. There's also the question of how much contrast do you have in the gas versus the dust, right? So many of these gapped ring systems, the gaps are not empty of gas, right? They may have a higher dust contrast, particle contrast, right? So I think say the default story here is that the rings have twiddled Saturn or sub-Saturn mass planets that are making a modest perturbation to the gas surface density that's enough to trap the dust, or use a strong structure in the dust, a modest structure in the gas. It's not enough to make a circumplanetary disk. And that, I would say, is sort of a possible ordering, given that both directly and indirectly, we think that the turbulence levels in these disks are actually quite low, right? So
right, and then that mass estimate itself places a constraint on the accretion rate that needed to be occurring at some time scale, which is to be checked against things. You're saying only Saturn mass planets. Okay, and any other questions for Phil? Please, Ethan.
So another question, I think you touched on this a little bit during the talk, is what would be the implication on sort of like the moon populations around giant planets? Let's say like with JWST, we see let's say 5 years we detect a comfortable population of exomoons. How would that help to test the possibilities of circumplanetary disk around giant planets?
Yeah, so I mean, I guess the sort of obvious thing I would say is thermal mass depends on h over r cubed, right? So So if you go inside, Jupiter, then conditions help you, right? So if you're imagining giant planets that can be seen in transit surveys, so there's the recent system that's been looked at with JWST, which may have moons, maybe moons are going to be detected. It's like a 1,000-day period, so that's already inside that of Jupiter. So anything there and closer in is in a more favorable CPD formation circumstance, right? So actually, going away from like direct imaging to sort of transit detection of moons is putting you in a more favorable place in parameter space based on what we would say. So that's one thing. I think the other piece of physics, which is the part which we've worked a little bit on, which I didn't talk about, is these disks. When you do form a disk, the material is sort of coming in vertically and impacting the disk quite close to the planet, relatively close to the planet. And so then, if the disk is really really thin, which is very unlikely to be, is rarely the case, then it is sort of accreting in the inner part and basically stationary in the outer part. If it's a little bit thicker, then it actually flows outwards at the midplane. So that is a sort of interesting regime for potentially building up dust and solids in the disk. And Konstantin Batygin and Morbidelli had a paper a few years back that kind of emphasized that aspect of the physics. And I think that is actually, given that these disks are quite puffy, even if they exist, I think that probably is actually an important kind of consideration, sort of qualitatively in the right place.
Mm-hmm. So it's easier because it's H/R scaling. It's easier to form your disk when you're in the inner region.
Yes.
And
of course, the radiative physics might work in the other direction, right?
Yes.
But in terms of just the basic, are you massive enough?
Mm-hmm.
Then
and gap opening. I'm trying to remember if that.
Well, that will also be easier. That will also
mm-hmm.
be easier.
Mm-hmm. Right. Well, I still wonder why, there is one very clear detection. The PDS-70C is, it's a very significant detection, right? So there should be, lots of detections. So what is special about PDS-70C? I mean, you mentioned 2 planets and maybe a bit of a deeper gap. Seems strange that how many systems have been looked for on the same level?
I mean, I think quite a few now, right? So, but I think if you look at, of course, many people have tried to estimate inferred planetary masses, right? And so the substructure estimates, sometimes the error bars do extend to a couple of Jupiter masses, right? But those are typically quite large error bars, right? So and it's quite degenerate, sort of for the reasons we've been discussing with the assumed alpha, right, or the assumed
mm-hmm.
turbulent physics, right? So I think I think let's say a possible explanation is just that really thinking 3050 AU. You need to be quite far along the mass function of giant planets, and there aren't many giant planets, right? Mm. Now, obviously, the second question, which goes back to the kinematics thing, those sources where there's evidence for kinematics, sort of again by definition, really, are pushing the higher masses, right? So those are the ones where I think there's the most tension, right? If you see a kinematic signature that you think is a planet, that probably says it's already more than Jupiter mass, mm-hmm. right? And so those really are in the regime where we would say we should be having CPDs. Mm-hmm. So not directly seeing the protoplanet there is. So I think my understanding, I've not seen this data, is that there's some sort of ongoing JWST surveys and data for some of those systems which maybe have not found protoplanets. And so if that becomes a firmer question or firmer result, then I think that will raise extra
Mm-hmm.
questions about what's going on, with the kinematics or how the luminosity is.
Mm-hmm. Can you remind me, PDA70C, don't they have a recombination line as well?
There is an H alpha. Yeah, there's an H alpha detection.
Is that useful for, I don't know, accretion rates, which can be compared to?
Yeah, so I actually had I had a figure up on one earlier slide. I can give it, but basically the accretion rate, it would be sort of consistent with what you would expect. So it's
that tells us it's not too dusty around.
Yeah, PDS70C sort of basically does fit with the simple picture.
But you can see down to the boundary layer.
You can see down to the boundary layer or the magnetosphere or whatever, whatever's going on in that system.
Yeah, I can probably chime in a little bit on that front, since I was before this, I was writing a paper about PDS70. We have some new Hubble observations. There is the system itself is also quite strange, right? The B shows a brighter H alpha, brighter volumetric luminosity, but there is no clear disk detections, right? There is some dust near B, but it's not quite at the location of B. So why we see apparently brighter, a faster accretion if, let's assume H alpha is correlated with the accretion rate, but we don't see a clear detection of the disk around. That's also looks quite strange to me.
Well, we're getting near the hour, but you mentioned one final topic, which with Rebecca Martin. Do you want to just flash up?
I can just flash it up.
Could I ask a quick question before we talk about
yeah.
Please.
So I just want to ask about this next generation observations. I'm wondering if you think if we looked at any of these substructure disks with band 10 at even higher resolution, if you think we'd see any circumplanetary disks, because I know, a little bit of angular resolution goes a long way. That's, I guess, question one. And then, when NGVLA comes online, we'll get better angular resolution at centimeter wavelengths. We might be able to, overcome optical depth in these inner disk regions where maybe the conditions are more favorable for circumplanetary disks. I don't know if you have thoughts on either of those two prospects for finding more of these.
Yeah, I mean, I guess I think both of those are really interesting questions, and I don't have anything very concrete to say. I mean, I think the question of how these disks, when they're present, capture solids and how much solid material there is involves some other physics, and other people have looked at it. It's very interesting. I guess I feel that it's certainly possible that the disks might end up being sort of overabundant in solids compared to the protoplanetary disk, right? So it may be that that going to longer wavelengths is quite favorable here, right? There's also potentially a different collisional environment. Things are all going to be a little bit different, right? So the maximum particle size might be different, and so forth, right? So I guess generally I like this idea of having more having more wavelength coverage. I think is tremendously powerful, and I think actually some of the next bit of ALMA potential, I think, is a lot in that way, right? Now we've sort of seen all the substructure, right? Really, from many perspectives, knowing something about the maximum particle size maybe would be the thing we would like the most, or I would like the most.
Mm-hmm. Great. Well, did you want to just show us this?
Yeah. So this is just a set of simulations. These are even more idealized. So these are just a planet in a binary potential. We feed gas to the circumplanetary environment disk at small scales and just watch what happens to it. The temperature is set here so that these are all circumplanetary disks, but with different thickness. Okay, so top panel is really, really thin, 0.1, going to thicker structures. And what one finds here is that sort of somewhere between 0.2 and 0.3, you get a change. So for thinner disks, the outer part of the disk remains confined within the Hill sphere. So it tries to expand, but the tidal forces keep it keep it penned in. But if you get to thicker disks, then actually it just flows back. So so even when you get a circumplanetary disk, often it may be thick enough, but actually it's not really an accretion disk in most of its regime. It's actually more like a sort of cyclic flow where gas is flowing in fairly close to the planet. Some of it is being accreted, of course, to conserve angular momentum, but quite a lot of it is actually just flowing back outwards and ultimately rejoining the protoplanetary disk. And as I was sort of saying, the key part of physics of the Vatican Morbidelli paper is that if you consider a dust particle in that sort of disk, its natural tendency to spiral inwards under aerodynamic drift can in some cases be balanced by the fact that the mean flow is going outwards. So it can kind of sit there and more material can build up, and maybe that's got something to do with satellite formation.
And can you remind me then, when a planet is accreting, the net change of angular momentum would cause it to go one way or the other in these disks? Or is that going to be impacted by any of
So directly, it isn't going to. Yeah, it's not going to be a first order thing, right? I would say, right? I mean, this is its own interesting question, right? So there would be potentially both a dynamical and a thermal contribution to a migration torque, and I think it's a separate and difficult question of how far inside the Hill sphere you have to really go to measure that correctly, right?
Okay, well, we'll have to have that for another topic maybe sometime. Very good, then. Let's thank Phil again for a great talk and discussion.